Today, I have with us Dr. Avinash Singh. He is currently a researcher and lecturer working at the University of Technology in Sydney, Australia. And this is also where he obtained his PhD in neuroscience and CS. So, Dr. Singh, could you tell us a little bit more about your background? I'd love to hear your story.
Thanks, Robert, for having me. I'm a lecturer at University of Technology, Sydney, where lecturer essentially means assistant professor here in Australia, which is equivalent role. And I come from the background, which is a kind of mix of computer science and later stage in neuroscience, which is I have very keen interest in. And because of background in computer science, it gave me quite a interesting background mix of where I can do something called translational neuroscience, using basic neuroscience knowledge, transform into an application. And that's a kind of a good connection I get because of BCI and neuroscience. I did my PhD, like you mentioned, here in Australia, which is a kind of a collaboration between Australia and one university in Germany as well in the US. So I got quite exposure in BCI technology as well, particularly with so many different funded projects with my ex-supervisor. I work in BCI particularly. So BCI stands for Brain-Computer Interface, where my work is especially rely in non-invasive BCI, means I don't do implants. I don't open the skull of the people to put the electrodes. I simply use EEG, sometimes fMRI. fMRI is a MRI scanning machine to collect the data, maybe record the data and create a BCI kind of setup with the help of that. So that's sort of my background. In addition to that, I'm actively advocate future technology. Sometimes people also call those activation as a transhumanism. That's another direction I touch here and there, time to time, outside my research space.
Sounds like you have a very interesting background story, and you're bringing a lot of knowledge from computer science into the neuroscience space. I was wondering what initially got you interested in neuroscience or neurotechnology?
That's a very interesting question. And whenever I try to recall why this might happen, I'm always very keen on human behavior. That's might be first reason why I got into it. But a while ago, I met Dr. Kevin Warwick. I don't think he might remember me. Kevin Warwick, known as a first cyborg. He is a professor in University of Reading, last time I checked. Pretty popular professor during that time, I'm talking about 15 years ago or so. He has an implant on his hand, and using his implant, this is the neuro implant, and he is able to communicate with the surrounding environment within his lab. When this happened, I was already exposed to so many sci-fi BCI movies, of course. And then I saw this in action, and I find it super interesting. And I was so keen that is it possible to create something like that? And maybe that's one big reason I kind of first attraction toward neuroscience to understand human brain and use such information to interact with surrounding. It just fascinated me a lot. And maybe that's the reason I decided during my master's itself that I want to do some work in this field. So I started with my thesis in master's, just jump straight into BCI, although I have no background. And that's the challenge I took, that I don't have background. That's why I get a chance to learn a lot. And then I did following a PhD, which is an interdisciplinary neuroscience, where I got computer science, but I focus my PhD on neuroscience alone. So that's where I get into this field. So I think major credit goes to Dr. Kevin Warwick to inspire that's possible, and maybe so much inspiration and motivation somehow from the sci-fi movies as well. Maybe one of them is Matrix. People might be thinking why Matrix is BCI, because core of all these movies somehow is a BCI, because if you look at the Matrix, they have a part where Neo has to go and sleep and plugged in back of his brain. That's a BCI. That's no other technology. And that's kind of project you into some virtual world, which is again Matrix. If you look at that, and if it's possible, you can think of so much possibility maybe with the BCI. But of course, that's like and long-term goal with most of the BCI technology out there. But that is somehow fascinated me a lot. And maybe that's why it keep fascinated me and keep driving me every day.
That makes a lot of sense that some of those factors would have combined push you towards this field. I had a few follow-up questions. So what kind of devices did Dr. Warwick control in his lab with this implant that he had?
He has some sort of implant on his hand. Now, this is not muscular implant, no. It's more of a neuro implant, but on his hand. That when he start trying to think, moving hands, those signal can project into opening the door and closing the door of his lab. And he's not so active anymore, as I know in the research, but those are like very early work and I came across. And that moment, that's enough information for me. Oh wow, that's so amazing that he can do such kind of interaction. Now there are so many similar work you can find. But the best part, like I said, it was not muscular or EMG, what we call. It's not EMG, it's not a muscular signal, it's an implant, it's an actual neuro implant on his hand, and that was very interesting. Might be I'm wrong, which I might be missing some information because I never went and read his paper and I just jump into the field, but that's what I remember when I had interaction.
Following up on your journey to jump into the field, you mentioned that you jumped in with not a ton of background knowledge of the space. And so I wanted to ask, was that a tough transition? And do you have any advice for somebody nowadays who might be wanting to make that transition too? Maybe they have a lot of their education in a different field, but they've recently heard about neurotechnology or BCIs and they want to make the switch.
Well, specifically for me, I took few courses, something around psychology, which has nothing to do with BCI, but it's good to understand human brain. And when I doing my PhD, I also took a lot of subjects around neuroscience, fundamental neuroscience, to understand how human brain work, not just behavior and cognitive science point of view, also biologically how everything works. And to be honest, biological part was super complicated for me. Maybe because I come from computer science, which is very logical field, logical in the sense it's a mathematical, but when you switch to things like a biological direction, it's complicated. That's what I would say. It's complicated. And I also face a lot of challenge there. That's a challenge anyway. So if you want to learn, you have to take that challenge. But having exposed to those subject, those knowledge, give me quite of insight, which is might be super important, I think, if you want to go into the field of neurotech or even brain computer interface or something around that. Because once you have that background, your ideas, your fundamental understanding directly apply to what you're trying to achieve in BCI. Recently, I mean, in last few years, BCI becoming a buzzword and lots of people, lots of researchers jump into this field. But what they have is only a data. They're trying to create BCI with that without having a understanding behind the data. So there's a bit disconnect. And because of this disconnect, what you're hoping to achieve from the BCI is not able to achieve by those researchers. So if someone interested to switch into this field, I think they should go through a proper background, fresh up 101 in neuroscience. That's very important. Without that, you can use EEG, you can use fMRI, you can have a lot of data, download online, lots of data. That's true. But without having that basic knowledge, I think there's quite a struggle what you're dealing with. Brain data is not same as camera data. It's not same as muscle data. Brain data is really vast and a lot of information is within that. And that information can be only extracted when you have understanding what's going on behind the data in the experiment in the brain.
Yeah, absolutely. That makes a lot of sense, how it's super important to understand the neurobiology that's going on behind all of this data that's being created. And as you mentioned, there's lots of layers to the brain data. There's lots of dimensions to it. And sometimes if one doesn't understand the biology or the neuroscience that's causing these data outputs, they might be missing out on some of what the data can give them. And so another question I had for you is, you have, along with some other researchers, you've called for standardization in the BCI research community. And can you share a little bit of detail with our audience as to what inspired this call for standardization, and as well as If the standardization is achieved, what impacts can it have on the neural engineering field? And then what are some of the key roadblocks to achieving this standardization?
So I'm part of two standardization committee with IEEE. So IEEE is a engineering organization. They are very popular to create standardization that apply pretty much everything around us, and then generally picked up by some other agency, for example, FDA, if you talk about US or somewhere else in the different country, their own standard organization. Why we get into this approach? Not me, it's not started by me. I was one of the contributing person or member in the committee. We came across that BCI, of course, is vast, right? There's lots of things happening, but there's lots of miscommunication, miscommunication in the form of terminology people using. So there's the same word for same thing in different way people reporting in your literature or online research papers. For instance, there's a one phenomena called P300 in BCI or in cognitive neuroscience in general. And somewhere you can read this called positivity, P for positivity. Some people call it just P3. Some people call it P300. Some people will call it a positive peak at 300 milliseconds. So there's a multiple way of talking it. I understand because I have a background, but if someone getting into this field, specifically with non-neuroscience background, is multiple terminology kind of confusing to put together and try to understand what this data is about. So that's one big reason. We want to unify this bunch of different terminology out there so that we can define them and standardize them, or try to use only these terminology to convey the same message all over the world when you say sharing your research. Second reason was when we share our data in BCI field. So I try to compare here computer vision, our data in the computer vision. It has been shared by all over the world and potentially is one of the most advanced technology out there. We are using camera, now we are talking, we have a background blurring technology perfectly work. There's a camera to capture the car number plate and so on. And they all are in application by some of the organization, government or non-governmental. But BCI, which is there since I think 100 years, really. I mean, at least the brain data is almost 100 years. In fact, this is the really 100th year since the first EEG has been introduced by Berger in 1924, and this is 2024, so it's almost 100 years, exactly 100 years actually. Although so much data, but unfortunately the progress versus the data produced outside or neuroscience knowledge is still a significant gap in there. And the bigger reason behind the gap is those who want to use the data, let's say a machine learning researcher or artificial intelligence researcher, which is becoming a more and more interest. Like I mentioned, without having a knowledge, it's difficult to translate, but you do not expect that every single one also go and learn neuroscience either, right? So why there's a gap? The gap is because the data shared by these researchers all around the world doesn't really convey the proper information to the researcher who's on their side, computational neuroscience or AI researcher. So we also trying to kind of bridge this gap by introducing some sort of framework that contain all those necessary information that you can feed into a tool that anybody can write that a tool, and that tool kind of create a data set for a researcher who's a machine learning researcher in a way that this researcher can generate very quick result in, for example, classification result or accuracy result. And then same result can be compared with any other researcher somewhere else in the world, and they can compare their result. Currently what's happening, you have this data, someone run it, get some results, but those results is difficult to compare with someone else somewhere else in the world because they don't follow the same structure, they don't follow the same way processing the data, inputting the data, and so on. It's very data unification problem, really. Although it's BCI thing, why BCI? Because it seems like it's a very important field nowadays. So we are trying to create this framework that can tell you exactly what you need when you're feeding information into your, I don't know, machine learning model or AI model. And we trying to create this framework as comprehensive as possible with respect to BCI. So that's what we're trying to achieve in this standardization. So we're trying to standardize the framework. We're also trying to standardize the unified terminology. So these two major goals. And in fact, we also publish few papers around that for people to provide feedback. Also, we publish models. So if you search unified brain computer interface model, I think you will find few papers around that. And this is all came from this standardization group. And we're hoping to make it even bigger sometime end of this year. That's a one goal behind that. Well, second is actually different thing, so we can talk about it later. That's the whole idea behind the standardization committee we have at this moment from IEEE. Hopefully, all these company you can see coming along in BCI, they may adopt that, because if they adopt that, it become more and more powerful in terms of sharing what we call fair principle of sharing the data around the world, and people can compare the information, people can improve the information, whatever happening with respect to BCI, and that can collectively progress the BCI much faster than currently it is.
First off, I'll make sure to share these papers and models that you mentioned, like links to them in the show notes. And yeah, that framework that you described seems like it could add a lot more accessibility to the field, a lot more reproduce. I think it's just important to get as many people working on BCIs and neurotechnology as possible. And if there's more accessibility, then there'll be more new ideas and more scientific debate. So definitely excited to see what happens next with this standardization framework. Another question I had to ask dives a little bit more into the technical side of BCIs. I was wondering if you could tell us a little bit more about your past work with Neuroadaptive BCIs.
So BCI, of course, there could be multiple kind, right? When I say multiple kind, people or academics, researcher divide into two major kind, or I should say three major kind: active, passive, and reactive, where active means you actively thinking and controlling things. One of the example of that, motor imagery. Reactive is things like something called SSVEP, which is a steady state visual evoke potential, where you look at the flickering and then your brain react to that flickering you're looking at, and you pick up those signal and use as a BCI. SSVP is one of the example. There are many other. And then there's something called our passive BCI, which is my favorite one. Passive BCI essentially means you don't have to actively control, you don't have to actively look at something, but you still can use your brain's signal to do something around you. And that's where Neuroadaptive is a sub-component of passive BCI, which is I'm super keen on. Why, again, passive BCI? Like I say, it's not actively required your effort to control and interact, but at the same time, you have a more information coming from your brain that you can feed into surrounding environment. So Neuroadaptive BCI, like the word suggests, is a neuroadaptive. So what we do in this field, or what I do in the field, is a relatively new term. If you look at around, it's not so popular yet. But fundamental idea essentially use the brain signal and let the surrounding adapt accordingly. So this adaptation could be adapt to your mood. This adaptation could be adapt to something called conflicting situation. This could be adaptation to your, let's say, mental workload or stress as well. So for example, I have a one work, again, this is all published work, so it's accessible to anyone. It's called Neuro-Adaptive Physical Human Robot Collaboration. So think of a situation, someone gave you a robot to control, a robot which is a collaborative robot. So essentially you have to control it, and robot also have control, like a half-half control, 50-50 control. And in that situation, when you might be interacting with such a robot first time, and let's say you want robot to move into direction X or direction Y, and robot move in that direction, but not as expected as you think. So there's a bit of a disagreement between your expectation and what robot is doing, right? So there's not smooth movement between you and robot when you're collaborating. That's where you can use the brain signal. And I call it prediction error negativity. We use that brain signal from frontal part of the brain and passively keep feeding into the robot the human is interacting. And what this robot does using those information, try to adapt as much as possible the forces coming out of the robot, or stiffness coming out of the robot, or resistance coming out of the robot, in a way that minimize this prediction error. So that's very simple logic. And we use this system to let robot adapt to human essentially, or that's what we call neuroadaptive. And the similar way, other example, which is related to mental workload, where continuously accessing the mental workload and let your surrounding environment. For example, this is one example of the work we were doing in the past with air traffic controller, which is very high workload job, highly stressed, short time, you have to make decision and so on. So let's say this is the dashboard in front of you, and we using your brain signal continuously to access that how much workload you having at this moment. Do you have a mental workload beyond the baseline, too much or too little? Because when the workload is too high, human is not so capable of making good decision, and there's a chances of error are very high. And if his job is like an air traffic controller, the cost of such a decision could be very, very dangerous, fatal essentially. Could be the plane landing or taking off, right? Like we saw unfortunate event recently in Japan, for instance, where the two planes collided to each other. So think of a neuroadaptive system here where mental workload is keep assessing, and once mental workload is too high, the brain information informed to the dashboard, which is, let's say, AI enabled. I mean, also have a capability of making a artificial intelligence based decision. So instead of making you decision, AI kind of giving and taking over more decision. So it's like a balance. So when you are not capable of taking the best decision, your machine learning or AI system taking more decision and so on. So again, this is a bit of neuroadaptive environment. And this could be applied literally anywhere where adaptation is needed. But robots and workplace environment are two key element or two key important scenario. And what I imagine this kind of work could apply, I always try to give this example where, let's say you're learning a bicycle very first time, and this system, maybe you're gonna take 3 hours to learn the bicycle, riding a bicycle, but using such a system, maybe that 3 hour become just 15 minutes, because now bicycle also learning or adapting according to your need. And so you very quickly start riding the bicycle. So the range of potential application of neuroadaptive BCI. And essentially I see the future where people have this system, and wherever they're passing through, the surrounding, it just adapt according to human brain. And that's what neuroadaptive brain computer interface is all about.
That's a super interesting concept, and those projects that you were working on with it seem to be really useful applications of this neuroadaptive BCI idea. I did have a quick follow-up question on the prediction error part that you were talking about earlier. So is the prediction error, is there some sort of signature of like an error having occurred, and then you work to minimize that neural signature?
That's right. So whenever there's a mismatch between your expectation versus what actually happened in the world which you're interacting with, human have a neurological feature that it generate an error. Error is just a signal captured in EEG, and I believe you can capture fMRI and other devices as well, which is essentially negativity in the brain signal. I mean, in other words, it's a biosignature or neurosignature. You can see very clearly happen around 150 millisecond to 250 millisecond once you expose to such a situation. So pretty quick. And this all happen in this part of the brain, frontal part of the area of the brain, also known as a monitoring or cognitive monitoring control part of the brain. So essentially everything is controlled by here. And this part of the brain essentially send the signal to other part of the brain what to do, how to tackle such a situation. Actually, whenever we learn something, this cognitive conflict all the time happen. It's a little bit like a surprise, but it's not a surprise essentially. It's just a mismatch. Kind of override your existing knowledge and you keep learning. We keep adapting. That's what neuroplasticity is and all those things is about. So we human keep adapting, and the reason behind adaptation is somehow is a cognitive conflict or prediction error. But so much adaptation, so much prediction error maybe make you tired and fatigued as well. If I ask someone to keep lecture for 6 hours a day, it's very, very boring, right? Can't take it. It's too much workload. Similar effect. So, and that's where the whole concept come from. So it's possible to measure this in within 200 milliseconds, this prediction error, every time you're exposed to a situation where your predicted outcome doesn't match with actual outcome, and you can see this error. And this happens in very tiny settings to a large setting. So robot is a great example, bicycle is another example, or a mental workload is a slightly different direction because we are not talking about prediction error, but any situation where you have expected outcome versus actual outcome and there's a mismatch, you will able to see prediction error. So it's that effective. And it's a continuous happening, continuous thing, which is only, I think, can be measured by EEG, because EEG is only that fast that can measure 200 milliseconds, not fMRI, no other devices. Maybe FNIRS, which is another near infrared as well, that can measure such a signal.
Yeah, that makes sense. With these signatures happening so quickly, you need, a modality that can pick things up just as quick. And another follow-up question I had on that is, what do things look like on the machine learning side for this? Are the machine learning paradigms that are able to kind of adapt with time, are these reinforcement learning? What kind of machine learning is used like on the other end of this?
Reinforcement learning is the most common scenario, and the work I just mentioned, Neuroadaptive physical human robot collaboration, is all around reinforcement learning. So because you don't know what to adapt, right? So you also have to learn what to adapt, because you don't know what is bothering your brain signal that it's producing prediction error. You can only guess, and you just the best guess, but maybe still there's a tiny bit here and there that you have to tune to make it consistent with your expectation. So reinforcement learning is a way to go so far, but it's also possible to simply use different category of prediction error as well. Although you are adapting to human brain, but human brain is still learning. Human brain is also adapting at the same time. Might be slower than reinforcement learning, but it's also happening same time. So it's possible that second time when you get prediction error, it reduced slightly, but it reduced not because of your reinforcement learning, but you just adapted yourself as a human. But reinforcement learning still is the best way to go. And one of those interesting, because this is cognitive conflict is not like a 0 and 1 kind of thing. So it's a range. Because it's a range, so not just any reinforcement learning, but it's called deterministic probability-based reinforcement learning is one of the best one I came across so far, if the terminology makes sense. People also call it DDPG in short. That can be used with the brain signal. And it's important to understand the reinforcement learning as a field generally happen or executed a lot with simulation, because you need a lot of repetition again and again and again so that reinforcement learning can learn. But I'm talking about human plugged in real time while reinforcement learning try to learn. And of course, you can't ask human to continuously sitting there and let reinforcement learning use your brain signal and you keep controlling the robot, for instance. So that's a bit of a challenging aspect with working with reinforcement learning where human is involved, but seems like it's becoming more and more common, not just in this kind of work, but lots of LLM, which is another popular direction the whole world is pulled in. LLM is used with machine learning and reinforcement learning where human feedback is used as well. When I say human feedback, essentially more of a behavior feedback, like you telling machine, okay, this is correct, this is not correct, actually with the score and with your computer or with your mouse click. So again, you see, it's very similar kind of approach, but think of a situation where you can just use the brain signal to do that, because those signals are more objective as well. those signals are instant as well. And that give you even more reflective answer what's going on when you expose human to certain stimuli. Could be LLM, could be robot, could be bicycle, could be self-driving car, could be an interaction with a psychologist, counselor. So that's another interesting project which I'm doing with Neuro-Adaptive BCI, where we're using this system with psychologists as well. So psychologists can make a statement very, very effective way that can directly hit the patient in a way that positively improve the interaction between them, or session become a good between them.
Well, thanks for explaining all that background on reinforcement learning. And yeah, it seems like it's being used in a lot of different exciting ways lately, as you mentioned, from LLMs all the way through to BCIs. I definitely see how that could be a little bit of a limiting factor on the reinforcement learning, whereas in other situations you can run, hundreds of thousands, millions, maybe even billions of simulations to help out the reinforcement learning. But as a single human, you can't really do that many rounds of practice. And then you have the reinforcement learning, algorithm learning, and then you have the human brain learning at the same time. So a lot of moving parts there, but definitely exciting work and exciting research, and I'm also excited to hear about the app in the therapy realm as well.
Yeah, those are very interesting application possible with, and not just there, there's some other range of other project happening. Some are still embargo, so can't talk too much about that. But Neuroadaptive have really bunch of potential direction, not just limiting controlling. I mean, BCI is just about control interaction, right? But to be honest, it can go well beyond with the passive BCI, which is, we can't think about it too much. And it could be our everyday application with every human around us. I mean, like us, which is maybe not very good with the active BCI because possibility of mistakes and possibility of bad signals and so on, that can all be avoided in the passive BCI. The reason is I'm saying only this because when it's a passive BCI, possibility of taking care the mistake, error, and bad signal is much larger. I mean, you can tolerate more poor quality of signal, you can tolerate more poor quality of detection, and so on, because it's a passive. It doesn't affect you directly, right? But when it's an active BCI, if you want to move hand left and right, or you want to go forward or backward, the BCI doesn't work very well. That's what happened in most of the cases. You feel a bit frustrated because you want immediate response. You get an immediate feedback, and that feedback is not what you're expecting. So you don't like it. And maybe in short term, excited to use it, but in the long term, you're like, oh, I don't want to use it. It doesn't really work. And that's what happened with most of the active BCI and reactive BCI as well. But it's a passive BCI because human is involved, human brain is involved, but human not getting feedback right away, or humans, whatever feedback coming to human is based on BCI or not BCI is not quite clear. There's a boundary is quite blurred. So it's more possible application out there with a neuroadaptive BCI than any other kind of BCI.
Yeah, that makes a lot of sense. The neuroadaptive BCI paradigm can open up a lot of avenues for usage of BCIs in lots of different cases, as you mentioned, rather than just very specialized ones.
That's right.
And then another question I had for you was, I've seen that you've done some work with regards to neuroethics. Can you expand a little bit on your role in that work, and what were some of the key ideas you were working on in the neuroethics space?
So this is also again with IEEE, but more specifically IEEE Brain. I would encourage everyone to go on their website. There's lots of resources on there for BCI interest people or audience. What I'm doing in neuroethics particularly is trying to create, this is another framework, if I use the right word, that how BCI can be used in workplace. Now, workplace is a very interesting environment compared to environment which is your home or wherever your own self-control environment, like your home, your car, you're playing a game or whatever. But workplace is an environment which is essentially attached to some sort of a reward, which is a salary in this case. You are more tolerant toward following what boss asks you because you need that work. So you are more obliged to follow certain things. Now think about a neurotech or BCI technology used in the workplace, then it's more high chances you give a consent to let them use it. And now once you give a consent, essentially it's possible to use those neuroethics, well, neurotech and BCI technology to measure your performance, to see how you are performing, to categorize based on your skill set and so on, and so much avenue in there. And once it happens, the discrimination and all sort of other phenomena start provoking as well because of those issues. Now, like I said, because it's a workplace, you're more likely to give a consent, and more likely to you give a consent, it become more widely is possible to use, and more widely is possible to use mean bring up all new sort of issues ethically possible. Who own the data, what kind of data information also can be extracted from the collected data you are doing, discrimination based on your skill set, your performance, and so and so on. And maybe, who knows, maybe based on that, it's also possible to decide how much to pay someone based on their performance, which sounds very dangerous in a way that, or ethical in a way that nobody want that kind of sort of thing. For example, if two people working in an office and maybe a certain day, one perform very good and other maybe a little bit down compared to the first one, and because of that his salary get cut just because neurotech telling this information in a monitor to your leader or to your boss that how much you are performing a job. So that is where this all come from. We are trying to create some sort of a guideline, if I say so, where we want these neurotech companies as well as workplace who may interested to use neurotechnology into the workplace go through the guideline to understand what kind of ethical concern or potential ethical issues may arise because of use of such technology into the workplace. And even they want to use it, what are the best way to utilize such a technology without exploiting the relation between employer and employee, without exploiting the case where employees just because he want to make money is more easy to give a consent to let them use any sort of technology they want, including implant. You never know. So this is where it all come from. And we are in this neuroethics. We are trying to develop this neuroethics framework for workplace since last couple of years. We are very close to publicize it very, very soon to get a feedback from public as well, what they think. But that's the major goal. This is a framework, this is a guideline just to inform, just to educate these agencies, which is employer, employee, neuroethics company, and so on, so that they can use the technology. If they want to use the technology in the workplace, it's more safe and ethical way. And like I say, this is more common than we think, just because sometime when neurotech has been used in a workplace space, it's also possible that employee also sign some sort of a contract that doesn't allow them to talk outside as well. For example, I mean, although defense or military or soldier doesn't quite come under the same as a workplace, but in a way still is a workplace, a little bit different kind, not like a usual workplace like we do. But neurotech is already harnessed a lot on the soldier by getting the data from them, by asking them to do something which might be not so ethical from neuroethics point of view. And so this is already a case, and this is getting more and more around the world, more and more company kind of pushing to get the best performance or best output from their employee with the help of neurotech. I mean, camera is already used. There's other tech is already in use, but they also want to harness the brain. And that's where the boundary between just simple monitoring to become really invasive, really intrusive monitoring become a big concern. And that's why we're trying to develop this guideline. And hopefully this guideline adopted by, again, agencies, and then they can be pushed to what we call, like in Australia here, we have something called a agency which control how the workplace should act, how workplace should tackle the security and ethical issues. They adopt this policy, and then all the company also have to follow up with the policy to align and to consistent with that, to minimize any kind of concern. That's the whole goal behind neuroethics for workplace, which I'm working for. And I'm the co-chair of this committee. So me and there's one more person from US. We both are working, trying to draft, and so many volunteer organization and so many neurotech companies also coming us to give us hand to understand how this might impact, what are their plans with any companies out there. They're trying to push this such a technology out there. And there are actually, interestingly, so many companies already going into that direction, because that's a very lucrative market, really, where so many companies are interested in. So that's a goal. Let's see how it goes. But I think these discussions are needed. That's what important. And maybe this is one of the first guideline may encourage and invoke more discussion and framework in the future as well. But this is the one of its kind so far, as I know, on neuroethics.
And I think I've heard of situations where places have started using neurotechnology in the workplace already. And as you mentioned, there are these risks related to privacy, data rights, discrimination, and much more. And so I'm glad that you and others are thinking about this, and that a framework is being built out, or guidelines are being built out about this. And I'm excited to see what eventually ends up coming out of that work. And then another quick question that I had for you was, so in addition to the neurotechnology research that you're involved in, you're also involved in boards and think tanks and advocacy groups related to longevity and transhumanism. And so I was just wondering, how do those all connect to the neurotechnology? And yeah, if you can just give us a little bit more background on those spaces.
Transhumanism or longevity, which I also kind of fall under transhumanism, is a concept, philosophical idea to transcend current human being in terms of muscular, physical ability, mental ability, or whatever, or all the possible physical part of our body, transcend into higher version, essentially create a human 2.0, if I say so. That's a philosophical idea, that technology we want to have that enable us to transcend into a higher version of us, in mentally, in physically, and also that's where the longevity also come from, where you're not just able to live, I don't know, 70 or 80 years, but you can live as long as you want. So it's an idea of liberty, essentially. It's an idea of giving you a power, giving you a possibility that you can choose how you want to deal with your body. You want to go and live longer life? Go on, go ahead. You want to extend certain ability of yourself. So enable such a possibility with human body is a goal of transhumanism somehow, or at least it's a philosophically, that's what we want. And how I'm get involved in this, I think one big reason is BCI itself. I think BCI is a very clear-cut idea where we want to extend our ability to control things with the human brain signal. This is sounds like a sci-fi idea, and not just sci-fi, it's already become more and more closer to what's out there. I mean, company like a Neuralink, which is keep pushing the boundaries of implant and so on, so that you can control Tesla itself, right? Or you can even play the music back to your brain and so on, and you can also deal with all kind of disorder. This is not different from transhumanism. And that's where, when I see the BCI as a whole, or BCI in next 20, 30 years, I can see it's directly related to that philosophical idea, which is a transhumanism. So I spoke highly in that. I mean, what we do as what we call ourselves transhumanists, that's a word we use, which essentially we trying to propose and project this idea to general public to educate them in a way what this odd ideas is all about. And essentially what we do within this activity, and which I support actively as well, we try to tell these ideas are not new. This idea is not harmful. This idea is simply giving you a power, maybe in the future, to decide what to do with your body. And I personally believe human. For example, if we have to travel Pluto, right? Which might be not a planet anymore, but let's say we have to travel to Pluto, which is like a several hundreds of years of travel from the planet Earth. And human body is not capable of doing that because we are just limited with our age, our lifeline, which is 70 to 100 maybe maximum, or sometime even 110, which is very, very rare. But then you have this transhumanist technology or future technology alone that enable you to live bit longer. That was possible, and that let you kind of travel all around the space or in this galaxy or beyond galaxy as well, just because you are more capable. Or you could live under the water because you can modify your lungs and your nose and your breathing, all apparatus in your body so that you can also breathe under the water, and so on. Like I say, it sounds like a sci-fi idea, but really we are already a transhumanist. I mean, people have implants. They're already using with the implant. Cochlear implant is one of the most common one. This is like a millions of people already have that. Brain implant becoming more and more possible than ever before. Maybe in next couple of years, maybe again, thousands of people already have a brain implant as well. Healthy people, not even people with some disorder or some sort of a physical limitation. So that's what attraction come for me, and maybe that's the one reason I'm very keen on. In addition to that BCI, I think a concept of mind uploading, which kind of resonate a lot with me, maybe based on neuroscience background. So that's where the longevity, or I call it digital immortality, essentially, where you can copy your brain into the digital machine or silicon machine, where your brain can access all the information like LLM model and can make educated guess. And you are always alive in digitally. So you essentially never die. But then people will ask the question about consciousness and other ethical issues as well. I fully agree with that. But that's another attraction. But again, you see, it's all related with neurotech for me, at least, because I'm looking at human enhancement, more capability from cognitive capability point of view or mind uploading point of view. Or like I gave you the very first example where you can plug in on the back of your head in your spinal cord and you can project yourself into a virtual world, like a movie like a Matrix, or even movie like a Avatar, and so many other movies really, where this brain projection is very common. Or if you can upload the brain, then essentially you have a power to access all the things before. Why uploading brain is interesting? Because this might be a concept where, I mean, biologically, even you extend the human life, maybe there's still possible that human ended in an accident and body just burned, or someone get in accident and you still people could die even though you have a extended human life. But it's possible to back up your brain in some way so that you can be kind of, again, this sounds like a sci-fi concept. And if I follow again, give an example of a movie or program here. So I think there's something called altered carbon, which is kind of fascinating ideas here, which echo what I'm talking about. You continue back up your brain and you just bring back, upload and download your brain into a physical or non-physical body so that you can interact with the world again. So that's another longevity concept or digital immortality concept with respect to that. So this idea excites me. Possibility, although, is far, far, far away because of limitation of technology we have around us. But somehow, wherever is a hope, there's a possibility, right? And that's what it is all about. Maybe it's a driving force as well, which I think maybe one day become true.
Yeah, based on your explanation, that makes a lot of sense how neurotechnology ties in with all of that, with the longevity and the transhumanism philosophy. And as you mentioned, some of this stuff sounds like science fiction today, like going to Pluto or living underwater or something of that sort. But who knows? As technology keeps on evolving and moving forward, who knows? Maybe that will become possible someday. And it's kind of exciting to think about. Another quick question I had, we kind of touched on it a little bit already, was so what do you see as your predictions for the field of neurotechnology over the next 20 years? It seems like some of the things we were talking about in the last question might be a little bit further out than that, but in kind of like the medium term, what do you see as some of your predictions for the field of neurotechnology?
What I really believe, I think non-invasive BCI still has a have hold better future because implant, I'm talking about current implant technology like Neuralink or Synchron, which is from Australia itself and now is in US. And these two company kind of doing a lot of interesting work with the help of implant or what they call it, minimal implant or minimal invasive technology. Sometimes they call themselves, like a Synchron call themselves minimal invasive because it just need a nerve to your nerve from the back of your brain to send those electrode or put the electrode in. And Neuralink kind of company which can just sew the electrode in the, and then they created this machine that can do this all the stuff, and so many other company which is also focused on implant. But because they are implant based, I think although they have lots of potential, what they can do because of good quality of signal, good possibility, they not just can read the signal, they can write the information as well, what we call stimulation. They can stimulate the brain cell as well, neurons as well to do certain things. But same time, I think if you look at the general public, people like you and me, do we want to have implant? I'm not so sure about that. I would prefer more non-invasive technology than implant. Now, with non-invasive technology, what we have a EEG and similar devices out there that may enable similar neurotech, what we hoping from Neuralink and Synchron and so on, other companies. But they also have limitation. These non-invasive technology have significant limitation in terms of what they can measure, right? So I think what's going to happen in next 10-20 years, I can see definitely implant going to open up lots of interesting neuroscience directions, what's possible out there. But ultimately, I think it's not an implant which is going to take over all these BCI tech. It's a non-invasive one. It just we have to create a bit more effective non-invasive neurotech, which does not exist, unfortunately, at this moment. Or we're gonna go into direction which is completely super invasive actually. So invasive, what I say, you open the scalp, have implant, but I'm talking about super invasive essentially means you inject the electrode into your blood cell. They are nano electrode and go over your scalp, spread over your scalp and your brain, and then send or emit the signal out. I think that might be another potential future. And to reach that goal, neurotech, well, not neurotech, nanotech needs to push forward the boundary. And there are very, very early work already happen in this area. And again, why I'm saying the current invasive technology might not hold very significant future because they can implant, you can implant and very specific part of the brain. They still can't spread. The major key of neuroscience or neurotech is still the whole brain, which only possible with non-invasive like EEG or FNERS kind of technology, or a nanotech-based technology that can send those nanosensor and just spread all over your scalp or all over your cortex. So these are like a two extreme direction, but nothing in the middle. I think we might go more on nanotech in the coming future, although there's nothing come out. There's no official company I have seen around which talk about that because it's a wave of, everyone riding on this neurotech wave, and all those companies just talk about new implant. And like I'm also saying, this implant very helpful for non-healthy people, but might be not too much beyond that. And that's what I'm talking about. That's where the future holds. A technology, unless it come to the consumer market where healthy people are easy to accept them, if that's not happening, might be not a future. And why I'm saying non-invasive is much better future because I've seen a patent application from Apple company. They have a earbud with some electrode that can go in your ear. And maybe they can use this information to control the volume of music or change the music. I think healthy people like you and me are more easy to accept such a technology instead of having an implant, unless implant is super necessary. So that's where might be we go ahead. We might unveil lots of interesting thing with the implants, but in the end of the day, it's a non-invasive technology which might win consumer market. and that make the application become more widely accepted among people like us. And in hopefully in next few years, we start seeing some nanotech as well, which is I think the ultimate neurotech supposed to happen in the future and unlock all the potential of neurotechnology coming in the future. But at the same time, very dangerous, of course. Now, one thing I want to highlight when I say nanosensor or this non-invasive one, it's important to understand we already take a lot of drugs, like a medicines, which already does this job, right? So taking a pill that can go and dissolve in your blood and you spread over your cortex and start emitting signal, and you start immediately get connected with the computer, and then later that dissolve, so it dissolve in your blood cells. So after a few hours or I don't know few months, the effect disappear, and then you get and take the pill again to get it activated again. I think that's what I'm hoping a neurotech will produce, and maybe that's the future. Short term, well, not short term, we're gonna see such application more. I think, well, not application, but some technology like this more. And the long term, I think that's a way to go as well.
That metaphor you gave regarding the medications helps give a good idea of the scale of how small these electrodes very well might be in the future. If somebody nowadays just thinks of, for example, like swallowing or injecting an electrode, it might make them nervous. But if it's so small they can't even see it, they might be more open to it. So I can definitely see where you're coming from there. Sounds like there's exciting times ahead in space, and I'm really interested to see what happens in neurotech, and I'm also interested to keep an eye on your future work coming out in general. I really appreciate you coming on today. And before we sign off, I just wanted to ask, could the listeners contact you for further discussion after the episode? And if so, what would be a good modality to reach out to you with? And what kind of things would you be open to talking about or discussing?
I love to discuss ideas. Always happy to talk with the people who have idea, discussion, encourage discussion, because this bring more ideas into the play. I love open for that, open for collaboration, always in research, particularly with the companies and academics. And the best way to reach out to me, I think LinkedIn, I'm pretty active in there and pretty quick to response. That's, I think, one of the most something between formal and informal way to interact with me. But there's always an email as well. That's a bit more formal if you want to reach out in that way. So I'm open for any way you want to reach out to me, and happy to talk, happy to discuss, happy to collaborate.
Well, sounds good. And thanks again for coming on. And I really appreciate it. And, looking forward to keeping in touch.
Thanks, Robert.